Okay, let's get started. Is my mic on now? Or is it? No. Is it on now?
Yes. Yeah.
Okay, great. Okay, so we reached the two last 45-minute lectures. I thank you all for coming. I can see not so many here today, but that's okay. I guess maybe some of you prioritize this just to do the assignment. I think I will try today to maybe leave some time at the end so you can ask questions about the assignment and we can have a kind of maybe a general discussion about all the topics throughout the course, and maybe you can give me some insights about how it is to be a student in these generative AI times, or maybe whether actually learning about what is under the hood of everything deep learning based, whether that makes you like better at using generative AI, I don't know, but I would like to have that discussion. So this means that I will probably omit some of the details in the slides, and if you want to understand some of the details that I omit in the slides, then just come to me after the lecture, and maybe we can even arrange a special session. I think some of it is, I included it just to make it kind of self-contained, and I think it'll be a little bit tough on you if I go through all the calculations. But I will try to go through the main things so you get the main ideas, and then arrest me if there's something that you think is really important for you understanding things. I mean, that's fine. I think we'll have time for that. Yes, so where I left you last time was kind of when we almost made it to the end of deriving this lower bound on the log likelihood for the hierarchical variational autoencoder. So I've kind of gone a few slides back to just summarize where we were. So in the hierarchical variational autoencoder, we introduced these kind of T+1 layers of latent variables, of stochastic variables, and we organize them as a Markov chain. So we start with kind of set 0 as kind of our base, and then we condition each of the next ones on the previous set in that chain. And then when we introduce the variational distribution in order to calculate this lower bound, then we introduce it to have the same structure as the generative model, and this is just convenience because it makes us able to write the elbow, the lower bound, in a very structured way where we have three terms. One, we call that the reconstruction in kind of the lingo in diffusion models. We call this the reconstruction. This is like the expectation of the log likelihood with respect to this variational distribution for the last latent layer. Also, the likelihood, remember, is only conditioned on the last latent layer. And then there's what we will call the diffusion term, and this will be clear today why we call this the diffusion term, but that is like all the term that arises from all the conditionals in our chain in the generative model. And then there's finally a prior term, which measures, like in the regular variational autoencoder, measures kind of the deviation between the prior, the simple prior, Gaussian IID prior, and then the variational distribution for the first latent. So the way that we turn this into an algorithm is that we handle the expectations we have here over the variational distributions. We handle those with sampling. And now it's a little bit more complicated than in the regular variational because now the set at a certain layer depends on the set at the previous layer, right? So that means that we have to sample the whole chain, all T+1 layers. So we do that by first drawing a sample from the initial layer. So we can write it like this, but what we do in practice is that we assume that this Q is a Gaussian, So we have to calculate the mean value and the standard deviation, and then we have to call our normal distributed random variable on our computer, and then multiply that to the standard deviation element-wise, and then we get the first C, and then once we have, and then I also a little bit of notation here. Theta denotes parameters, is kind of shorthand for parameters in the generative model, and phi is shorthand for parameters in the variational distribution, just to distinguish these two. So you can see here I put a phi mu and a sigma phi to indicate that these are the parameters of the variational distribution. And you can also see that I sometimes forget to put them, so you have to also sometimes read it out of the context. So now we have set 0 here, and then in order to get kind of set for the next layer, we have to plug that value into this mu and sigma functions here together with the data x. And then we have to kind of get some new random variable, normally distributed random variable, and then we get the set for the next layer, and then we can iterate on that all the way through to set 1, and then we can use that set 1 to also kind of calculate this term in the same spirit with the sample. So we kind of plug in the sample here. Yes. So that's kind of how we do it. And now, because we have kind of isolated all the stochastic in this kind of sigma here, then we can actually take this expression and apply backpropagation with respect to both the parameters in the generative model and also the parameters in the variational. And now this kind of view of this as autoencoder can be thought about like this, that first we use this kind of stochastic encoder to get set 0 up to set 1, and then the decoder is that we plug that set 1, final set 1, into the likelihood function like this. Yes. And once we have trained the model, then we can actually kind of, as I said last time, throw away the variational distribution and simply use our generative model to kind of get data by kind of doing this kind of iteration over the latent layers. So we start first by drawing a simple normally distributed set 0. We plug that into this distribution here, and then we draw the next set, and so on. We keep on iterating this, right? So this is actually also when you think about like when you get ChatGPT to generate or Stable Diffusion to generate an image for you, then it's actually performing something like this under the hood. Yes. Okay. So that was kind of where we left last time. So now we will kind of, and this is where it gets a little bit, I mean, I think there's nothing, it's not like, this is like mathematics like proofs and so on. It's more like calculations. That's kind of the level of math I can do. But these calculations can still become a little bit cumbersome and a little bit hard to follow when you just have the teacher explaining them to you. So I mean, I recommend if you really want to deep dive, try to sit and kind of redo the calculations. Maybe the first time over, do it for like one-dimensional data so you don't have to carry around a lot of indices and so on. But I will kind of walk you through some of these steps and maybe omit some of the others. So in order to actually kind of show that we can take this kind of limit, where we take this kind of the difference between the different layers to 0, or equivalently having infinite amount of layers, we have to go a little bit more into detail with the exact expressions. So as you know by now, when we use variation autoencoders, we like to use Gaussian distributions because they are kind of simple and allow for very simple expressions. So this means that if we want to look at one term in this kind of diffusion laws, right in here, let me go back, right in one term here, so one just for one particular value of L, then I can use some simpler notation. This is always nice. A good advice if you want to do math is, do some simpler notation. So instead of writing T subscript L and T subscript L minus 1 all the time, I'll just call the first one T and the second one S, right? I don't lose anything, so that means that what I want to calculate for one of the terms looks like this. And now you can see I use this notation that everything related to the generative model is theta, and everything related to the variational distribution is phi. And now I also try to use colors. I excuse if anyone is colorblind. I hope you can see the difference a little bit. I think there should be someone here who's colorblind statistically, even though we're not so many today. If you are colorblind and you say that I use a bad color palette, then come to me afterwards and advise me about better colors. Anyway, so you can see now that I try to here say, okay, everything with P is theta and everything with Q is phi. But everything is Gaussian, right? And these mu and sigma, they are like, we approximate those by neural networks, right? So they take as input for the oh yeah, I can see I make an error here. There should be no X here, sorry. This is an error, copy and paste error. No X here. I mean, the generative model, of course, cannot depend on X. So I'll correct that and upload a new version. Yes, so you can see this neural network here, forget X, right? So this is a neural network that takes a Z as input. It also takes a T as input, right? So it actually knows what layer it is in. So it has, let's say that Z is d-dimensional, then it's kind of the input here is d plus 1 dimensional. You can also look at the code in the assignment for one and kind of confirm this. And in this case, for the variational, we additionally also condition on X. So let's say that we let the latent dimension be and the data dimension be d, then this input to this neural network here is 2D plus 1 dimensional, and so on. Yes. So we have two terms we want to calculate. We have the expectation here of the log for P of ZT given ZS, and we have the expectation of log to Q of CT given CS comma X. And then with a minus sign because it's in the denominator here. So let's take one at a time. We'll start with the easiest one, and that is the log Q. And here you can see the calculation. So remember that a one-dimensional Gaussian let's call it like this. That is like 2 pi sigma squared right, and then we have to take the log of this. Then we get here minus half log 2 pi sigma, and then we have the log cancels this one, so it will be minus, and I forgot half here, c minus mu 2 sigma like this. So you can see now when I take the log, I get the first term I have here, that is simply this term. I have a sum over I, that's the sum over the dimensions because we have independent variances in each direction. And the second term I get is this coming from this term here. And now I need to make, I need to take the expectation here, and then I use the chain rule of probability, so I can write that as Q of CS given X times Q of T given ZS and x, right? And then you can see that if I perform this expectation here on this term, I simply get the variance again, and that cancels exactly with this, so here's just a 1. So this will be, if there's d dimensions, then this term will simply be minus 1/2, and then d times 1, and that is d, so it will be minus d/2 in total. The other term here still depends on, here you can see the term doesn't depend on set t, so that term will disappear, and then only have an expectation with respect to set s, like here. And I cannot do that analytically, I have to do that with sampling, because this can be a very complicated kind of nonlinear neural network dependence on ZS. But I don't care about that, because I believe I can do sampling and it can be a good enough approximation. Okay, so this is the first half of the results, getting the expectation with respect to Q of log of the blue part here. Now I will turn to the more hard one, which is the log P expectation. And the most difficult part in that one, you can see I can do kind of the same triggers here. The most difficult part here is now that I don't, this has a mean value of mu phi, but now I subtract here mu theta, right? So it is kind of the wrong mean. And how do I cope with that? I'll show you that later on, but the final result is simply that instead of getting, the variance like before, then I now get the variance plus the difference in the two means between the blue and the red one squared. And this is kind of a very fundamental result. You'll see that many, many times. I here have the calculation. The trick is that I take this expression inside here, and then I subtract the same value and add the same value. And then I can show that the cross term, when here is kind of one term plus another term, and I square it, right? Then I can write it out as the first term squared plus 2 times the 2 terms multiplied, and then the second term squared. And the nice thing here is that the cross term disappears. You can look at that yourself. I don't want to spend time on that. But the final result is this nice result that I get the variance. Now it's the variance of Q, because that's the one I take the expectation with respect to. And then I get this sum of the means squared. Sum of the means differences squared. And since it was the P distribution, then it is kind of sigma theta here. And in the numerator is sigma phi. Yes. Okay, let the dust settle, and we are then end up with the final result here, that we have like the first term is like the difference, kind of the log differences, or kind of just the log of the ratio. And then we have this second term. Now I just kind of reintroduced the 1 in this way. And it looks not so nice. But then you can do one thing. You can try to make the model simpler. You can say, okay, now I want to kind of just do a modeling choice that I set these two variances. So here's a squared missing, or I should remove this squared. You set these two variances to the same. And then everything becomes much simpler, because now you can see you take the log of 1, that is 0, and also here you have the difference between the two variances that will cancel, and we end up with this very nice simple term, saying that this kind of, you can call it path, this kind of transition contribution to the elbow is simply this difference between the mean squared, kind of normalized by the variance of the generative model. Okay, so let's plug that into, no, let's do something even more. Let's try to write the mu and the sigma in a particular way. And this particular way is not, of course, kind of random, but it doesn't kind of remove any generality at all. But you can see now we write mu for the generative model as like a residual network. You've probably seen that in the course, right? That you actually kind of pass through a set, and then you kind of have some kind of extra term, and you can do the same for the variational distribution, and you can also kind of write this sigma here in terms of this kind of square root of the difference between the layer indices, right? And this delta t is 1 over t. So you can see now I've kind of scaled this kind of offset here with delta t for the means and with square root delta t for the standard deviation. And this is not a coincidence. This is kind of what you need to do in order to be able to actually take this limit of taking t to infinity and then get kind of a finite result. Okay. So if we do that here, right, so remember this was kind of our result. If we kind of make these kind of choices, and this is also part of assignment 4.1, that you try to implement exactly these choices, then you can see from the numerator, you get these two sets here kind of are the same, right? So they will cancel, and it will only be the difference between f and g, and then kind of multiplied by, since we squared, multiplied by delta t squared. Here we have sigma squared, so we also kind of plug in that sigma, and we get the square of delta t, of the square root of delta t, so that gives a delta t. So you can see delta t doesn't go out. We are left with delta t here, right? And that's very important. Stop me if there's any questions, please. Yes, so let's go back to the original expression, because now we spend a lot of time on kind of massaging like one term in this diffusion term here, right? Now we can take that result and plug it in, right? And now we kind of introduce the sum over all the layers again, and we get this result, right? So this is kind of, it looks nice in a way, it looks kind of simpler. And we have this delta t here, right? And now you probably remember something from your kind of math courses. Now they come in handy. Some of you are computer scientists, so maybe you're not super happy about math, but now you can see actually we can use math for something, because we have a result from math, and there's of course a lot of kind of, proof, limits, blah, blah, blah. I'll forget that a little bit here. But if you have a sum like this, right, where you evaluate some function at different points on an interval, and you have this delta t, then you can show mathematically that actually this will become an integral once you take this kind of delta t limit to 0. So that means that actually we can write now the diffusion term as an integral over kind of continuous layers from 0 to 1 with this expression, right? So it means that actually now our latent variable is defined for each kind of continuous value on the interval from t equal to 0 to 1, right? So we started out first with a kind of regular variational autoencoder. Then we did a hierarchical variational autoencoder where we had like, okay, we do 5 layers, 3 layers, whatever. Now we suddenly go to infinite layers, right? but we can do that formally, right? So as long as we can define like a marginal distribution, this Q, you can see also now here the expectation is no longer on like two adjacent layers, right? It's only defined in terms of the latent variable defined at time. Now I just call it time t, right? So instead of talking about a layer index, I'll talk about a time. Of course, it's not a real time. It's like a position in the interval between 0 and 1. Yes, so I can now actually write my lower log likelihood lower bound, where I replace this diffusion term by this with the sum with this integral here. And this is kind of is a consequence that I have this delta t here, right? So if I had chosen another way of scaling, this can be shown pretty straightforward mathematically. If I had chosen another way of scaling the means and the standard deviation, this would not have been possible. So it's only something that is well defined with this particular scaling. And this particular scaling corresponds to what is called a stochastic differential equation. And that's one of the things I'll talk about in the next part. And these kind of terms, diffusion model, score matching, neural ordinary differential equation, and flow matching, these are like some of the techniques that have been developed the last like 5 years, or a little bit more, that are very popular in everything related to kind of generative image analysis or generative molecules and so on. So really kind of useful, flexible modeling techniques. Yes. So this is kind of the game plan for the rest of the time here. So I'll talk about diffusion models. I'll talk about score matching. I'll talk about neural ODEs. ODEs are like a version of differential equations that are not stochastic. I'll define that as well. And then I'll talk about also flow matching, which is a way to actually use essentially this kind of diffusion objective you saw before, but now to learn not a stochastic model, but a deterministic model. And then if you stay with me until the end, I will set aside some time for some final remarks and also time for we can have a discussion and I can answer some questions. Yes. Okay. So now I'll just come back to the elbow. I have replaced this sum over all the layers with this integral or this continuous layer index, and let's see how we would actually go about implementing this as an algorithm. Yes. So remember the way we would kind of evaluate averages in the good old days, right? That would be that we would define this kind of iterative sampling procedure. Let's see how that looks when we replace the mu and the sigma with this kind of other formulation we had before. And this is what is called the stochastic differential equation. So now we say, okay, I have a stochastic variable at time t, and I then can express the stochastic variable at time t plus delta t in terms of this stochastic variable at time zt, right? So this is like what also called like a Markov process, right? Because you can see that the stochastic variable a little bit later in time only depends on the stochastic variable at time t. So it's kind of the residual thing, so it has zt, and then it has this kind of what we call a drift term. This is deterministic, and then it has a noisy term, which is then scaled. You can see that this drift term is scaled with delta t, and the noisy term is scaled with square root of delta t. Right? And then we have delta t going to kind of 0 in a way, right? So that is kind of the stochastic differential, the differential equation formulation. Later on, we will come back to a model where we don't have the ODE, the ordinary differential equation, doesn't have this stochastic part. We can also write the generative model in the same way. Now, just instead of having G, we have F here. And actually, many times when we talk about stochastic differential equations, we don't write this square root of t explicitly. We then write it as dw, and dw is this kind of square root of delta t times epsilon, and this dw is then a Gaussian variable because epsilon here is a Gaussian variable, but then it has a variance which scales with the delta t. And this construction here is very famous. It's called a Wiener process. Maybe some of you have met it in kind of stochastic process courses. Yes, I just say these things to kind of connect with a little bit with the stochastic differential equation lingo. Yes. Okay. So let's turn this into an algorithm. Let's be a little bit more concrete, right? So if we look at the elbow, we have kind of some usual suspects. We have our likelihood function. We also have a prior for the first layer. These are easy to define, right? We will just use, for example, if we use these kind of binarized MNIST, we'll just say that this is a bunch of Bernoulli likelihood functions, and then set 1 will define the kind of the probability of heads, probability of a white pixel, and the prior is also easy. We'll just take the prior we used for regular variation autoencoder. It's also easy to define these the F here and the sigma as neural networks, right? That's like how we have done it with kind of the mean and the standard deviation in our regular variation autoencoder. What is harder now is that if you look at this expression, right, it's not so nice because we need to be able to actually find. We have to be able to compute expectations with respect to this Q distribution, right? So how can we do that? We can do it in the hard way. The hard way is that we kind of simulate this distribution here. We simulate the stochastic differential equation for corresponding to the variational distribution. That is not so nice because it means that, let's say we have t equal to 0.57, right? Then we have to kind of go all the way from C0 and take small delta t time steps, and then eventually kind of iteratively find a sample for this C for t equal to 0.57. So what we will always do in practice is that we will choose this stochastic process to be so simple that we actually have access to Q of set t in a closed form. And as you know, the simple distribution we have is always a Gaussian. And in the bonus material, some extra slides that I've included, you can see how to construct like a process here, how to choose G such that we actually get Gaussians for the variational distribution. So that means now we built like a construction now where we make Q simple so we can get these samples, and then we can actually evaluate this term here for any t, right? But it seems like it's still complicated because we still have to integrate over t. But as you know by now, we really love to do things by sampling. So what we can do now is to say, okay, if we have an integral from 0 to 1, we could actually write that as an expectation over the uniform distribution for t. And then, okay, here we have an expectation. Why not replace that with a sample? So that means that instead of trying to evaluate this integral, we simply draw a random t value between 0 and 1, plug that in, and then we use that when we evaluate in our computer program, evaluate this elbow here. So this is sometimes called simulation free, because what we consider as simulation in machine learning is actually kind of simulating from this stochastic differential equation here. Okay, so let's write down the algorithm, the pseudocode for the algorithm, hopefully very closely related to what is in the assignment code. So we have to define how many discretization steps we want to take. We have to define with a neural network the drift. We also have to define this G drift, but we do that. We have kind of been dictated from our choice of the variational distribution, such that it's a Gaussian for each marginal. We have to define this kind of sigma here, the diffusion. We have to define a prior. We have to define a likelihood function. And we have some data. Yes. So the way that we kind of sample from the stochastic differential equation is that we initialize it to some value. So we draw from our Gaussian, but in this formulation, this is kind of not part of the function. We give it at a c value, we give it a t value, and then we give it a delta t, and then we kind of just iterate this equation, right? So we first draw some Gaussian noise with variance delta t, and then we simply use our stochastic differential equation to get the next c, and then we kind of run this for t steps, and then we return c like this. So if we want to calculate the elbow, remember, if we go back to the elbow expression, right, it has 3 terms: the reconstruction term, this diffusion term where we replace the integral with just drawing one random t, and then the prior term. Right, so we have to put that into our elbow. So that means that first we draw a random value for t between 0 and 1. Then we draw 3 values of c for 0 to get the prior term, for t to get the diffusion term, and 1 to get the likelihood term. And then we use the expression we had before, so we calculate the expected log likelihood, approximate that with this sample. We approximate the prior term with taking the set 0 sample and plug that into this ratio. I just written it out as log p0 minus log q0, and then in the end we have the diffusion term, where here I sum over the dimensions of our latent variables. So this is quite simple. I hope you will be able to recognize this in the computer program. And finally, when we have trained the model, we can actually draw new data. We can draw a new image, a new MNIST image. So first we draw the first value, C0, from the prior, and then we use this function up here all the way from all the way to t equal to 1. So we have set 1 now in the end, and then we use our likelihood function, draw from that to get this, the final image. So this is the algorithm. Let me see now. Yeah, I can just go through this. This is also something you have kind of more or less seen when you ran the program. So in this example, you can see on this axis you have time, so the index, right? So here I've just done like an estimate of the training data. So the training data in this case is like a mixture. So this is the density of the training data. So I've just used some kind of standard built-in scikit-learn density estimator. And it's like a mixture of 5 Laplace distributions, I think. Then I can look at of qt given x and look at the density of that before training, and then you can see it's more or less like an identity, so it will just give me more or less the same distribution. And that's of course not good because I have a prior distribution here which is Gaussian, right? So the model will probably like to learn to kind of make the data look more like a Gaussian, make Q look more like a Gaussian. So the reverse also before training is that I kind of try to draw samples here from the prior distribution, that's a Gaussian, and then use the generative model using this kind of procedure here, to actually push that samples from the prior forward, and you can see it hasn't learned anything. They just end more or less at the origin. Once I've then run the training, you can see now that actually pushing data forward, that's the kind of purple lines. You can see it kind of moves from the prior distribution out and mimics quite well the distribution of the data. And you can also use the Q, the variational distribution, and you can see that it kind of starts with something that is very close to the data, and then it moves backwards and have something that is very close to the prior. Yeah. Yes, I think this is a good place to stop for now. Any questions? Yes?
I'm not sure I understand the simulation tree you take. Is it like sharing the parameters for each layer, or how?
Yes, okay, I didn't say that, right? But you can see it kind of implicitly here that F here is defined as a neural network that takes Z as input and T as an input, right? So that means that it's one neural network. But because it gets T as an input, it kind of knows, okay, I'm actually here now. So in this kind of simulation, you can see once it's trained, it knows it's kind of here, and then, okay, here in the beginning, okay, I should maybe move a little bit in this direction, right? But once it gets kind of higher T, it actually, because it knows T, it knows, okay, here I should actually move more, right? So without having the T dependence, it would not work at all, right? But it's a very nice way, and it's used a lot in neural networks, right? If you think about recurrent neural networks, it's the same layer you apply at each time point. So this kind of idea of kind of amortizing computations by giving extra information is something we use all the time in deep learning. And of course, it's also something that people who work with stochastic processes have done always, but then ideas occur many places. Yes?
Yeah, this is the generating part, right?
This plot is both, I mean, the red part here is sorry, I said wrong. The purple part is the generating part, right? So that is like I draw from my prior distribution, and then I take that draw, and then I essentially use this top thing here. Yes. And the red part, I don't have my glasses on, that's why I cannot read. That is like you start with somewhere at the data, and then you look at what is kind of Q, what is a Q all the time. Yeah, I will also come a little bit back. I mean, there's stuff I haven't told you yet. I'll tell you that next hour. There's also things about how you can actually make a stochastic differential equation that runs forward, and you can make the equivalent that runs backward. But that's a little bit more subtle, so that will be after the break. More questions for now? Yes, okay.
Yeah, so you have, through the slides, you had first, in the hierarchical, you had this, you had the elbow as a two-term of, let's say something, it's basically two terms, the KL being one.
Yes,
And
or 3 terms, yeah.
well, this, yeah, so you, here you have 3 terms. But
Yes,
but previously you had only 2 terms.
yes,
And is this just a rewriting of that same
yes,
equation?
yes, that's just a rewriting, right? Because if you have a joint probability and you write that as a chain, right, then there's like an anchor, you start it somewhere. And that is, the start is of course not conditioned on something on the previous step. And that gives rise to this prior term. But it's true that in the regular variational autoencoder, these two, the diffusion and the prior term, they are like collapsed into one. Yeah. Great. Let's have a break and start again. Okay, question? Yes? Yes. That's because maybe I will remove that next year. But this is the dimensions, right? So you can see this here. Fi here is the ith component of f is a vector that has the same dimension as z, right? So Fi here is just the ith dimension of that z vector, right? Maybe I should change the notation so I only work with vectors. I think maybe it confuses a little bit. That was just a choice I made when I made the slides. Yeah. So this sum goes like from 1 up to the dimension of this set. Yeah. Okay, thanks guys. I think it's wonderful. It seems like you paid attention all the time, and this is difficult material.